somewhat like a derivation on this. So let's study this so that using simple diagram to determine the mathematics related with this one. So again, we draw the single slit. And then this is a double slit. Single slit and double slit. So what we have is the light travel to here. And then each point S1, S2. We like to observe some places in here. In which cases there's a distance out there and distance is out here. So you consider the path in distance, path length distance. So in which cases this is we call P. So we like to find out the path length difference between S1P and S2P. So that's one we like to see the delta S2P minus S1P. Now as far as the wavefront goes, we like to say is we draw because this distance is far away, so we draw the perpendicular point here. So if we draw the perpendicular line here, that means at this point are the same phase. It propagates reach to here. And the distance are so far away, this length and this length are the same. So what is the difference is here is the delta. It's a delta, in which case it's considered as a path as the distance. So this distance, we like to say consider as the slit separation is D. And the distance from here to here, we like to say L. The distance L as compared with the distance between this S1 and S2, L is very, very large. L is very, very large than the S1, S2 separation. S1, S2 separation. So in these cases, we need some little bit what we call the trigonometry. Now this angle, we like to say is theta. If this is the angle is theta, so this angle is theta. So delta calculation is equal to d times sine theta. D times sine theta. So the path length distance delta is called, you can using optical path distance. So S1P is one optical path, and then S2P is another optical path. That comparison between the distance between them, that's the way. So when this delta equal to d times sine theta, that is a very important factor. Why? Because if you separate with a multiple length, that means they are in phase when they reach at this point. So d times sine theta is a determinant factor for this point if it is in constructive interference or destructive interference. When d times sine of theta equal to m lambda, then this is give us the bright And if the delta is equal to d times sine theta equal to half wavelength, m plus 1 1/2 lambda, that will become a dark fringes. Dark fringes. So, so what is the difference? Okay, now what we like to say is this. Like this. This is bright fringes. When these up and down and merging together, this is the light come from S1, this lights come from S2. Okay? Now, if this is, if they shift, right? If they shift multiple wavelengths, then they give us this is the lambda. That means the m is an integer. If m plus 1 is still shifting by one wavelength, so it's still the same. Now, S1, S2 in here, if it's a separation by half wavelength, so this is a half wavelength, okay? If this is a half wavelength shift, so this shift to here, so this one like that. Then this go like this. So in these cases, when this is a maximum, this is a minimum. When this is minimum, this is maximum. So they cancel each other. So in that cases, this gives us a dark fringes. And this one gives us a bright fringes. We have one experiment. We'll do the Young's experiment. We'll do the demonstration on this. So this is basically is called Young's experiment. So I would like to stop here today, and then when we come back Monday, we have a lot to talk about. Example 27.3. Chapter 27 is related with the wave optics. Wave optics basically is talking about treating the light as wave, propagation like a wave. So the first thing we have done is about 27.3. We done last week about the interference. That means that when the wave travel, you separate beam, and then you'll have interference, interreaction with the what we call the two separate source point. In these cases, the light is starting at one point. This is a light source, and it propagated as a wave, come down here, and like this, and then reach to this point. So the length of a point, a source travel, and another point is the length to travel, S1, S2. The separation between these two slits is D, and then reach to this point P. So there's a difference in the length in travel. This length have a special name, in which cases is called optical path. So the another difference is called OPD. OPD stands for optical path difference. Optical path difference. Optical path difference is equal to, suppose in this area, the medium is n sub 0. So optical path for the distance R2 is n sub 0 R2 minus n sub 0 R1. That difference is called optical path difference. So based on this optical path difference, and you can find out this is perpendicular, and this is optical path difference, delta. That is equal to delta, and that is related to d times sine theta. D times sine theta. So this is the key, and then if d times sine theta delta d times sine theta equal to delta. If it is m lambda equal to multiple of wavelength, in which case m equal to 0, 1, 2, 3, and 4, like this on. This will give us what they call constructive interference. This is give us a constructive interference. In the lighting, is called bright fringes. And then if you have the delta is equal to what we call m plus 1.5 lambda. This one, m equal to 0 to all the way 1, 2, 3, 4, like this. That will give us dark fringes. When it's constructive, it gives us bright fringes. When it is destructive, it gives us the dark fringes. So in the screen, you will see the fringes like a bright dark fringes. So you can, working this backward, the theta is low theta L. Here is the theta. This is the theta. And this is the y. So the distance from here to here is L. So y is equal to L times tangent theta, or approximately equal to L times sine theta. So from this equation, you will find out where is the spot. Where is the spot is bright, where is the spot is dark. But if you from another point of view, this two optical path difference right in the center, that is bright. Right at the center or location, that will be bright because the delta is equal to 0, so this will be bright. So the wave optics prediction is where right at the center here, the fringe is bright. But from the particle theory, the light travel here and then blocking by this by the cover by the slit here, so it will be dark. So between this determine is the light is wave or not. Huygens highly determined, say, according to this assumption or this experiment, Huygens said it has to be light behaves as a wave, and then good old what they call Thomas Young making performance on that. So you're learning physics from your point of view. Change subject, but you're learning all this interference, constructive interference, and destructive interference. So we usually in America is we say how you going to apply it. In China or Oriental, then we feel we are very happy. We understand this phenomenon and do a lab and demonstrate that go away. Okay. But in the practical society, in the lab facility, is hey, what you should do about this? Okay, how to take advantage of this constructive